السلام عليكم طلابنا الأعزاء. إن شاء الله اليوم محاضرتنا هي Sterilization of biomaterial. إن شاء الله محاضرة تكون خفيفة لأنه ما عندنا بها شغلات قوية. أريدكم تركزون على شغلتين مهمة، أنه كل Sterilization agent هذا هو المود اوف اكشن مالته، ونركز انه يا ماتريال اللي تشتغل نقدر نعقم به او نسوي sterilization بهذا الايجنت. Introduction. Biomaterial are required to be sterilized before use. If sterilization is not feasible, they should be properly disinfected. Sterilization is the complete elimination of all forms of microbial life, including highly resistant bacterial endospores. Disinfection is to eliminate the recognized pathogenic microorganisms with a chemical or physical procedure, but not necessarily to eliminate all microbial form on medical devices. Requirements for the sterilization. The effectiveness of sterilization process is measured by the probability of sterility for each product sterilized. The sterility assurance level or SAL، مختصرها اللي هي SAL SAL. هنا عندنا انه كلش الامور تكون جيدة لما يكون السال هو 1/1,000,000. يعني شنو؟ يعني أنا من أسوي sterilization لكل 100 مليون برودكت راح يكون عندي واحد من عندها هو ما صار بي sterilization، فهذه تعتبر انه الافكتفنس مالتنا عالية جدا. لكن أنا لما أحقق هذا الافكتفنس ممكن أسوي دامج للماتريال مالتي، خصوصا إذا كانت هي biological based، مو هي مثل ميتال أو سيراميك مثل التيشو جرافت أو مثل هذه البيولوجيكال ماتيريال. فهنا ال FDA انطتنا ابروفل انه 1/10⁻³ اللي هو يعتبر كل 1000 برودكت اذا عقمناه سوينا له sterilization راح يصير عندنا واحد غير معقم، فهذا يعتبر الافكتفنس مالتنا مقبول او جيد جدا. The sterilization should not cause any significant change in the material that would elicit an adverse response from the body. The sterilization should not significantly alter physical and mechanical properties of the material that would compromise the implant's function. Sterilization methods: heat and pressure. Dry heat. The dry heat sterilization destroys microorganisms by destructive oxidation of cell component. To kill resistant spore by dry heat, it usually requires a temperature of about 160 degrees centigrade for 2 hours. Dry heat sterilization is suitable for material that are heat stable, such as metal implants that might be damaged by moist heat, or for those that are impenetrable to moist heat. هنا شو نقصد؟ يعني احنا عندنا بعض الميتال او معظمها بالمويست هيت راح تؤدي لي الى corrosion ويا الهيت اند مويستشر، راح يصير عندي corrosion، فبالتالي اني بالميتال اروح للدراي هيت اتس بيتر. مثالها هو اكيد كنا نعرفه وشايفيه بالكلينكس مالتنا، هو الهوت اير اوفن. moist heat in the form of the saturated steam under pressure is the most widely used method to sterilize solutions and surgical tools. It inactivates microorganisms by the irreversible coagulation and denaturation of enzyme and structural protein. To kill resistant bacterial spores by moist heat, it generally required 121 degrees centigrade for 50 to 30 minutes. Moist heat is commonly used for sterilization of heat and moisture stable materials through which steam can penetrate, such as stainless steel implants and surgical tools. The parameters that affect efficacy of sterilization include steam, pressure, temperature, and time. The two common steam sterilization temperature are 121 and 132 degrees centigrade. أفضل مثال هو الأوتوكليف، وموجود بالعيادات كلها الحمد لله حاليا، واللي هي تشتغل على 2 بروجرام، اللي هو يا أما 121 أو 132. وهنا طبعا إذا قل درجة الحرارة الوقت راح يزيد عندنا، يعني احنا قلنا عندنا العوامل الاثنين مع ثباتية الضغط والستيم، البريشر والستيم. راح نتلاعب بالتايم والتمبرتشر، إذا قللنا التمبرتشر نزيد التايم. هي هذه الفاكتور اللي تأثر لي على الافيكاسي اوف moist heat. Ionization irradiation. UV radiation. UV radiation is used to control airborne microorganisms and surface decontamination for the environment of the biomaterial production and processing. The short wavelength UV light, 254 nanometer, disrupt the structure of the nucleic acid through the formation of the thiamine dimers and therefore destroy the reproductive capabilities of the microorganism. UV radiation alone is not considered to be an effective disinfection or sterilization method because of its poor penetration power, long treatment time, and the susceptibility to air movement. In addition, UV radiation damages many types of plastic. UV radiation may be incorporated as a part of the overall strategy for bioburden control and sterilization during any manufacturing process. Gamma radiation has been used as low temperature sterilization method for over a half century. The wavelengths of gamma ray are less than 10 exponent minus 10 meter, with frequencies greater than 10 exponent 18 Hz and energies at the 100 kilovoltage level. Gamma radiation has far greater penetrative power than electron beam. It is safe, cost-effective sterilization for a wide range of medical products like tissue for transplantation, pharmaceuticals, medical devices, disposable medical equipments. Gamma radiation kills microorganisms by attacking the DNA molecules through both direct and indirect mechanisms. Gamma radiation does not leave any chemical residues and does not impart radioactivity. X-ray technology for sterilizing medical devices has already been in commercial use for 15 years. X-ray emitted by electrons and are high frequency, short wavelength electromagnetic photons with a very broad energy spectrum. X-ray and gamma ray differ because of their origin and their energy spectra overlap. X-ray produced by linear accelerators can reach the megavoltage energy level and have higher energy than gamma rays produced by radioactive gamma decay. The maximum photon energy is the same as the kinetic energy of the incident electrons that are used to generate X-ray, unlikely gamma radiation. X-rays are concentrated in the direction of the incidence electron beam, and the angular dispersion decreases as the electron energy increases. The high intensity in the forward direction enhance the efficiency of X-ray utilization. The penetration of high-energy X-ray allows one to process large packages and pulse loads of medical devices with very good dose uniformity. The fast process, excellent dose uniformity, and better penetration than gamma rays or electron beam make the X-ray technology an alternative sterilization method for medical devices. Electron beam. Electron beam sterilization uses high energy electron beam from accelerators to irradiate biomaterials or biomedical devices in their final packets. Unlike photons, fast electrons have both mass and charge. Thus, the range of penetration of high energy electrons is limited and depends on their energy, the atomic number of the absorbing product, and its density. Electron beam inactivate microorganisms by the same mechanism as gamma radiation does. One of the advantages for electron beam radiation is that its high energy power can sterilize in seconds instead of hours or days compared with the other methods. It was shown that bacterial spores show greater sensitivity to electron beam than gamma radiation. Now, sterilization methods with chemical sterilant. Ethylene oxide. Ethylene oxide is bactericidal, sporicidal, and virucidal, and has been widely used as a low temperature sterilant since the 15th of the last centuries. Ethylene oxide is a colorless gas that is flammable and explosive. Ethylene oxide's microbicidal activity is a result of the alkylation of proteins, DNA, and RNA in microorganisms, which prevents normal cellular metabolism and replication, and thus renders affected microbes nanoviable. Ethylene oxide's higher activity in combination with the high diffusivity plays a major role in the inactivation of microorganisms. In ethylene oxide sterilization process, the major factors that affect the lethality of sterilization include ethylene oxide concentrations, temperature, humidity, and exposure time. The bioburden reduction increases with the increases of the ethylene oxide concentration, exposure time, and temperature. Humidity is another critical variable in ethylene oxide sterilization. In the range of the 30 to 90% humidity, the humidity does not have significant impact on the lethality, and sterilization efficacy decreases markedly below 30 and above 90% humidity. The commonly used operational range for ethylene oxide concentration from 450 to 1200 milligram per liter, temperature from the 29 to 65 degrees centigrade, humidity from the 45 to the 85%, and finally exposure time from 2 to 5 hours. Despite ethylene oxide toxicity and safety concerns for some sensitive material, ethylene oxide is the only acceptable sterilization method. In contrast to irradiation and heat sterilization that have deleterious effect on biological materials and polymers, ethylene oxide is compatible with a wide range of materials, and its penetration properties make ethylene oxide sterilization the most suitable process of the majority of heat and or moisture sensitive medical products. Sterilant solution. In addition to ethylene oxide, a few other sterilants have also been used for sterilization. They include formaldehyde, hydrogen peroxide, and peracetic acid based system, as well as other oxidizing agents using in liquid and gaseous uh, processes. Peracetic acid is a strong oxidizing agent, and its oxidation potential is greater than that of chlorine or chlorine oxide. Peracetic acid has bactericidal, fungicidal, virucidal, and sporicidal properties and has been widely used in medical disinfection processes. Peracetic acid used to sterilize heat-sensitive devices such as endoscopes and their accessories. Peracetic acid is unclear and colorless liquid and has a strong pungent acetic acid odor. It is commonly produced by the reaction of acetic acid with the hydrogen peroxide, and therefore peracetic acid solution contains hydrogen peroxide up to 25% and acetic acid up to 35%. Peracetic acid oxidizes the outer cell membrane of vegetative bacterial cell, endospores, yeast, and mold spores. A rapid penetration of peracetic acid into microorganisms and release of oxygen and free radicals critical for the oxidation and destruction of microbial enzymes are likely linked to peracetic acid sterilization efficacy. Peracetic acid methanol mixture could effectively inactivate viruses in bone and porcine intestine. It also works synergistically with hydrogen peroxide in microorganism inactivation. Peracetic acid strong oxidation property is critical to its sterilization efficacy. However, this property may also reduce the biological, chemical, and structural integrity of biological material. Similar to the peracetic acid, hydrogen peroxide also inactivate microorganisms, bacteria, yeasts, fungi, viruses, and spores through oxidization. It can be converted into highly reactive hydroxyl radicals which attack membrane, lipids, DNA, and other essential cell components to inactivate bacteria. Hydrogen peroxide is more effective as a sporicide than as a bactericide. Hydrogen peroxide appears colorless in diluted solution and is one of the most powerful oxidizer known. Hydrogen peroxide is naturally present in milk and honey to preserve them from spoilage. It is also the chemical that the phagocytes use to kill the bacteria that enter the bloodstream. It can be readily decomposed to water and oxygen spontaneously or by enzyme known as peroxidase process by living being. Formaldehyde is used as biocide in liquid or gaseous form for sterilization because it is toxic, mutagenic, and carcinogenic. Its use is limited. There is a new method in the sterilization like supercritical carbon dioxide. Dense carbon dioxide was firstly found to have the bactericidal effect in the 15s. The supercritical state is a unique physical state that is reached at a specific temperature and pressure combination defined as the critical point. Supercritical carbon dioxide exhibit properties of both gaseous and liquid physical state. It has the viscosity of the liquid and the transport efficiency of a gas, which will allow for efficient delivery with high penetration properties. The unique properties of the supercritical carbon dioxide make it an applying medium for sterilization. Its high diffusion characteristics allow for deep penetration into materials. In addition, it is non-toxic and can easily be removed by the depressurization and outgassing. The effectiveness of the supercritical carbon dioxide on microorganisms is related to the various treatment parameters, which include temperature, pressure, treatment time, and the use of the additives. Supercritical carbon dioxide can inactivate a variety of the microorganisms, but supercritical carbon dioxide alone is not enough to achieve an industrial level of the sterilization, which was, as we mentioned, Sal 10 exponent minus 6 of the same microbes, including bacterial endospores and the viruses. To enhance the inactivate of microbes, sterilants that contain pure acetic acid are commonly used. When supercritical carbon dioxide is used with the additives such as pure acetic acid, it can inactivate logarithm 10 of bacterial endospores on spore strips. Supercritical carbon dioxide treatment is compatible with many biological material, including bone and the cellular dermal matrix, and it leaves no toxic residues in the treatment material. It has been shown that the supercritical carbon dioxide with pure acetic acid sterilization caused little change in the biochemical and biomechanical properties of a cellular dermal matrix. Another new methods: gas plasma, ionized gases. There is multiple gases or many types of gases that use. The low temperature plasma method is considered to be promising method for some biomedical materials that are not compatible with the heat and chemicals. The advantages of the gas plasma method are shorter process cycle and suitability for more complex medical instruments, especially those contain hollow parts for minimum intrusive procedure. Gas plasmas are generated by exciting gas molecules with radio frequency or microwave to produce charged particles known as free radicals. Gas plasma process uses mechanism combine the action of UV radiation generated from the excited molecules and that of oxygen-free radicals. UV radiation causes lesion of DNA strands of microorganism, intrinsic photo disruption, resulting from UV photons breaking chemical bonds of the other microorganism materials to produce violet byproducts. Example: carbon monoxide, chlorhexidine. Reactive species within a plasma field, atomic and molecular radicals or excited molecules in the metastable state undergo chemical reaction with cell component to initiate spontaneous etching and thereby disrupt the structure and metabolism of the microorganism, yielding the final oxidation produce products such as carbon dioxide and H2O. The type of seed gas is an important variable affecting the effectiveness of the plasma sterilization process. FDA cleared the use of the hydrogen peroxide plasma sterilizer in the United States. Another gas plasma system uses acetic acid, hydrogen peroxide vapor. The hydrogen peroxide gas plasma system operates at 37 to 44 degrees centigrade and has cycle time of 50 to 75 minutes. Selection criteria of the sterilization method for biomaterials. It's summarized in this table. إن شاء الله هذه المحاضرة طلابنا الأعزاء راح تنزل البي دي اف، يعني هذا الباوربوينت بسيط لأن هي ما نقدر نسوي بها باوربوينت أو برزنتيشن أكثر من هذا، لأن هي عبارة عن بي دي اف وملخص وبسيط. راح ينزل لكم ويا هذا الفيديو وإن شاء الله يكون سهل عليكم، وأي سؤال أنا حاضر تقدرون تتواصلون وياي. Thank you for your listening.